So now for a little bit on energetics and energy diagrams. So what you learned in 152 was this diagram. The whole point of 152 was to study all aspects of this. So if you remember your kinetics section, what we were concerned about is how fast a reaction occurs. Well, that was largely dictated based off of your activation energy, which is the energy necessary to go from your reactants to your transition state, often shown as the double dagger. After that, you studied a whole bunch about thermodynamics and equilibrium and all those fun things. That's looking at this delta G aspect, the energy between your reactants and your products. You get different things describing what's happening at each of those cases. Mostly what we're doing in OChem is using those energy diagrams to give us an understanding of how our reactions work. They're the underpinnings behind how all of our stuff functions. So it is important to address some of those kind of basics. So we'll actually go backwards in the slideshow. Thermodynamics, whoops, let's go all the way back. Clear all that away, sorry. Thermodynamics in our Gibbs free energy. So Gibbs free energy is the difference in energy between our products and reactants. That's what we're seeing through in here. Okay, so you can get a delta G for the reaction. That's related to your KEQ, all that kind of fun stuff. Your equilibrium constant is the concentration of your products over your reactants, right? So when we think about thermodynamics, what we're concerned about is that balance within those. So we can make statements about the delta G for the reaction being less than 0, okay, which is that middle box. If it's less than 0, what does that ultimately mean? Well, that means that our products were more stable than our reactants. We can backtrack that all the way through using our algebra, all the way back through these systems to figure out what's going on with that. But ultimately what you need to remember is that if we're looking at a delta G less than 0, we're looking at an exothermic reaction, and if it's exothermic, your products are lower in energy than your reactants. Conversely, or also, however you want to phrase it, if your delta G is greater than 0, you're looking at an endothermic reaction. Your products are higher in energy than your reactants. And there's going to be varying things that are going to jump in here. For instance, in this discussion, we haven't addressed anything about how we get from reactants to products. Okay? And that's going to be a discussion of kinetics, which admittedly I don't have a nice slide on, but we'll throw it in there in a little bit. Okay? We could also tie in delta H and delta S and all that kind of fun stuff, enthalpies and all that. Not a critical deal. That's more 152 oriented, so don't stress a whole lot about it. But we will see these terms pop up every so often, and we can probably memorize our way around having to stress about them. So thermodynamics, again, was addressing that difference down below. Our kinetics is that upper portion. How do we move or transition from our reactants to become our products? Those kinetics are dictated based off of a rate. Our rate is dependent on a rate constant, and then it's dependent on some concentrations, held to certain orders. And for those of you being like panicking because you didn't want to have to remember any of this, you are responsible for it in OChem, but we'll see it in a very limited exposure, so don't panic straight out yet. I do want you to realize, though, that your kinetics is rate constant times your concentrations held to a particular order. Okay, so that is important. We do need to know that. And then our thermodynamics, when we're talking about thermodynamics, we're concerned about the relative energy of our reactants in comparison to our products. Okay, what is that proportionality? Okay, and I want relative, but I don't know how to show relative. Okay, so they're looking at different aspects. The kinetics is primarily reactants, so we do have a simplification there. We don't have to worry about our products so much. And then thermodynamics is where our reactants are with respect to our products. So when we go through and look at any reaction, we need to be considering aspects of our thermodynamics and our kinetics when we evaluate them. So if we looked at some reactions, if we look at water reacting with itself in an acid-base reaction, so if we follow our arrows, the electrons are being shared with that hydrogen, which means that first species is a base. The next one is going to be an acid. This is going to go through and produce some products. And we end up with a conjugate acid and a conjugate base, which I'm just going to do CB for conjugate base. We can look at Q's, delta G's, and all that kind of fun stuff. We could now also spin this out to an energy diagram, okay, where we're looking at our reactants, which is both of these, becoming our products. Okay, we have the ability to now layer these things into an energy diagram. So first off, we know that our reactants exist. Okay, since we don't necessarily know where our products need to be drawn, either above or below yet, we could just draw our reactants somewhere floating in the middle of our energy diagram. As the reaction progresses, so this would be known as our reaction coordinate, we're going to slowly become product. So our product needs to appear somewhere over here. Now the question becomes, what should the product be? Higher or lower in energy than our reactant? So we have to reference that. Well, to decide that, we could go through and look at delta G's and all that fun stuff. It's a positive value. Since it's positive, this means it must be endothermic, which means our product must be higher in energy. But what if we don't have all of those numbers? Because that's the beauty of OChem, is that we don't need the numbers to be able to come up with those predictions. Okay, so what do we have to do? We'd have to look at our products and compare them to our reactants. So we could compare acid to acid, and I don't like the color coding on that, so I can compare acid to acid, and I can compare base to base. If I've memorized some pKa's, I know that my acid, water, has a pKa of about 15.7, and my conjugate acid, H3O+, has a pKa of about negative 1.5. Okay? Negative 1.5 is significantly more acidic, which would mean, using the pKa argument that we've gone through, would heavily favor our reactants. Okay? And if we're going to favor our reactants, that means they must be lower in energy. If we look at the base argument, we could go through and look at pKb's. But again, the whole point of this was to avoid numbers, and all I've done is talked about numbers. So let's look and evaluate their reactivities. I'm concerned about the base strength of the water versus hydroxide. Okay, well, I'm going to use my ranking system for stabilities. What was that ranking system again? Sort of a rhetorical question. Please run through them out loud. Okay, hopefully we got charge, size, electronegativity. I'm going to always write as chi, resonance, induction, and then I'm just going to say OS. Okay, so we would need to evaluate those with regards to base. Well, what does it mean to be a base? A base needs to be an electron donor. If we're an electron donor, what would we expect our charge to be? Well, we would expect it to be negative because it has electrons. So if it is something negative, it should be a better base. So let's go through and compare hydroxide to water. Water isn't negative, so that means it is the weaker base. What does that mean for our reaction? It's going to favor our reactants. Again, we come to the exact same conclusion. Depending on which way we go through, we still end at the same result. Our products are higher in energy than our reactants. Okay? If we wanted to finish out our energy diagram, we could now go through and show a curve getting us across. Don't stress about the exact height of this. Okay? What I want you to be able to do is to compare this height to other heights of other peaks. If we don't have any other peaks, we don't have anything to compare to, so don't freak out about it. Just know that that transition state has to be higher in energy than both the reactants and the products, otherwise it's not a peak. Okay? So hopefully that makes sense, and we now have an energy diagram to represent this reaction. Okay? So, ta-da! There it is. And if we go through and look at this, Cardi has gone through and added a bunch of extra information, your reactants to your products, that delta G, that difference, products minus reactants, because our products are higher in energy, ends up with a positive value. We could quantify it and drop in all those numbers, but again, we don't need to. Okay, we don't have to specify that level of detail. Okay? So, how could we use that for other reactions? Say if we were going to compare the relative acidities of CH4 versus NH3. Okay? Well, if I want to go through and look at this, both of these are going to release an H+, because we're talking about them acting as acids. Okay? That H+ is officially going to get picked up by water, so we could go through, if we wanted to make sure that we had this balanced, and write this in as H2O positive. Yeah? So we're producing, in either case, H3O+. What else is produced? Well, I'd get CH3 with a negative charge on that carbon, or I'd get NH2 with 2 lone pairs, because it started with 1, a negative charge on the nitrogen. And I could now go through and draw energy diagrams for these. Okay, so let's just focus on the CH4 for the moment, okay, and that reaction. We're looking at reactants going to products. So again, I'm going to draw my reactants somewhere in the middle. Okay, I already have some answers on this, so I'm drawing it a little bit lower. And if we compare across this, we can ignore pKa's, and we can just say, well, let's look at the relative strength of the bases. We're looking at H2O acting as a base to go forwards, or we're looking at CH3- acting as a base. Well, if we go through and evaluate that, we can use the same rules that we've been evaluating: charge, size, electronegativity, resonance, induction. We can jump straight at charge. The negative is higher in energy, so that means our reaction should very heavily favor our reactants. Okay? So what does that mean? That means our products should be higher in energy, and I can draw my products up here. I can complete out my energy diagram. Ta-da! And I've now drawn my CH4 energy diagram. Okay, we'll clean up the bottom there. So now what happens when I go through and look at the NH3? Okay, so I now want to add that to that. Well, if I'm going to now draw on that reactant, okay, so in blue now, where should I draw that reactant? I want to draw it in a situation or in a place where I can see how it differs from the red one. So drawing it out where I've got it drawn way out there doesn't make any sense. I want to draw the reactant energy somewhere in this space. So now the question becomes is where should I place it? Okay, higher or lower in energy than the CH4? Well, let's go through and look at our reactants and make the comparisons. We're using water in both cases, which means there's no difference in energy according to our water. If we now compare methane to NH3, they're both neutral, they're both about the same size. Yes, there's a difference in electronegativity, but that difference isn't doing a whole lot to the overall reactivity. What does that ultimately mean? That means that our reactant for the NH3 is going to be roughly in the exact same space. So if we overlapped those colors, we're going to be getting red and blue going in the same space. We've got a purple system. Well, now let's move to our products. We move to the products, now we can see those charges. Okay, and that charge now appears. Again, we would expect our product energy to be higher in energy because it is charged versus neutral, right? Or neutered, whatever that says. So now the question is, where should it be? Should it be way up there or should it be under here? Okay, well, let's compare again those two species. They're both charged, but is that charge going to be a different energy in this case? Well, yeah. Why is it different? Okay. Nitrogen is more electronegative than the carbon, which means it's going to stabilize that negative charge significantly more than the carbon will. Okay? So if it becomes significantly more stable, where should it fall on our energy diagram? Well, that means the product energy should be lower, okay, for an H2. So what does that mean? If we now continued to draw out our energy diagram, we'd get something along those lines. Okay? And what does that mean for us? Okay, well, if I'm going to try and remove a hydrogen from CH4 and NH3, I'm going to remove the hydrogen from the NH3 first. Okay? Why? Well, one argument might be that we have a difference in energy in our products. The better argument, the activation barrier to remove the hydrogen from NH3 is lower than it is for the CH4. Okay? And that's what we're using our energy diagrams to kind of show and help us represent. In these cases, we don't need the energy diagram. The point of using the energy diagram is to set it up so that we have something that we can evaluate and think about and manipulate and use in more advanced questions. So Carty goes through and shows the exact same thing, and we can look at all of those individual pieces and how they stacked out. Of course, it looks like I color-coded backwards from what he did. Okay? But this is what we're trying to see. Again, the nitrogen becomes more acidic because the activation barrier to remove that hydrogen is lower than it is for the CH4. Okay? Why should it be lower? This is something what's known as the Hammond postulate. The transition state is closest in energy to the reactant or product that it is closer to. Okay? Which is kind of a silly statement, but really what we're saying is that peak is dependent on, the peak for our nitrogen is dependent on the energy for the product. The peak for the methane is dependent on the energy of the product, because these were endothermic reactions. If they were exothermic reactions, that's going to change our diagram around. Okay, so let's real quickly think about what that would mean according to the Hammond postulate. I can't believe I just walked myself into this. Okay, if we flipped this and went this direction, what does that do for us? Well, now those peaks, our transition states, are going to be closest in energy to our reactants. Since the reactants are the same energy, what does that mean for us? Okay, well then that means that the difference in the transition states is going to be relatively minimal, and we're going to have to see some other effect come in there to dictate where our products are coming from. Okay, don't stress on that with the Hammond postulate. Yes, it's important, but it's not important enough for you to worry about right now. Okay, and I believe that's all I've got on starting our energy. Yep, so I'll add a video here in a second.